Hello and welcome to another tutorial. In this tutorial, I'm going to continue the discussion on how to implement numerical integration. We're talking about one-dimensional functions at the moment in Java. So our functions of f are basically f of x, and we want to know how to implement those. And the method that we discussed so far was rectangle estimation based on uniform partitioning, and we said that we could have a forward approximation, backward approximation, or midpoint approximation, and in each sub interval we said that we can actually approximate the function, the value of the function, by a constant number. And then we did some examples. For example, f of x equals x, f of x equals x squared, and we were able to show that these functions are Riemann integrable, and we also found that we found the exact value for the integral from a to b. And then we said that this is basically related to antiderivatives of these functions and how the general or the fundamental lemma of calculus works. Now we're going to look into the numerical implementation. So first we try to do implement the rectangular estimation based on uniform partitioning, and we define first, just like what we did for root finding, we define an interface to enforce the fact that the input is a real variable and the function also returns a real function, right? So we define an interface that builds this contract with the user, with anyone who wants to use our code, all right? And we can define it as an integral function. This is the name of the interface. Or even better, we can just use the built-in function interface in basically Java library, the built-in Java library. And the way it works is that it takes two parameters. So it's a parameterized interface or parameterized class. And the first parameter is the type of the input, which we can put as double. And the second one is the type of the return, or the return type of the type of value of the function, which is also double. So we can use this, right? Any of these should work. And then we define a class that performs the summation, and obviously we should have some sort of stop criteria because we cannot sum over infinite number of terms. So it could be the number of terms. So we say that, okay, just sum over 400 terms or 200 terms. It could be the convergence. We could also implement a convergence test for the series. And if you recall, in the topic of sequences and series, we discussed this. We can implement the test based on the absolute error of the series as we add more and more terms, or we can test based on the relative error of the series, all right? Now let's head to Eclipse and try to implement these. So here in the Eclipse, I'm going to create a new project and call it the demo integral. And in the demo integral, I'm going to create an interface. Let's call it integral function. And here I'm just going to create a double value double x. So this is a function, and you recall, if we have a public interface, by default this method double value is going to be public and abstract. So these two are implicit here in the definition, public and abstract. And you already know the routine that we are going to use lambda expression most of the time. Use lambda expressions because that makes life easier, all right? Now, as I mentioned, there is also a built-in function in Java library, the function interface, but here I'm just defining an interface, and then I'm going to create a new class called integral. And in the integral, let's call this, actually let's refactor it, rename it with integral 1D, one-dimensional integral. Later we will have 2D and 3D integrals too. And here what we are going to have is we just pass a integral function. So integral function is func, and then in the constructor we're going to just pass in an integral function, func, and because this local variable has the exact same name as our global variable or class level variable, we have to make use of this modifier to avoid any shadowing of the variable, avoid shadowing of a class variable, right? All right. Now method. So method 1 is a rectangle estimation or rectangle approximation plus uniform partitioning. So we're going to say that public double get integral or integrate. For example, let's call it integrate, and double start, double end. All right. So how are we going to implement this? Is let's call this actually forward rectangle or rectangle forward. So we're going to implement the rectangle approximation based on forward summation. All right. So we create an array of doubles, double vals or f vals, or let's call this x vals. These are the beginning edge of each sub interval, new double, and the length should be endpoint. So here we're going to set the int as terms, num terms or number of terms. Let's call these terms. How many terms should we sum? So terms, and then for int I equals 0, I less than x vals, I plus plus. What we're going to do, x vals I, actually this should be x vals dot length, is start plus I times delta. So we have to also define our delta, double delta, which is end minus start divided by terms. All right, I times delta. This is the definition. We have n terms, and after finding the x vals, what we are going to do, basically we are going to create our summation, double sum equals 0, and then we're going to again write another for loop, I equals 0, I less than x vals dot length, I plus plus. Here we just say that okay, sum plus equals delta times func dot value add x vals I. All right, so we're just calculating the summation, and eventually we return the sum. Okay, so let's go and test this. Test, we create a main method here, or maybe let's go and create the main method outside that. So new class test integral, we want to have a main method, and in the main method I'm going to create or invoke test1, and in the test1 is going to be public or private static void test1, and in test1 I'm going to define an integral function, and we could also change this to integral function 1D. I think that's a good idea. Integral function func is equal to t goes to, for example, t. So let's first integrate a constant function, and then we define an integral 1D, integral finder, for example, which is new integral 1D, and we pass in our function, and then double result is integral finder dot forward rectangle from 0 to 2 with 100 terms. And let's make sure these are doubles, 0 to 2, 100 terms, and we're going to sys out the result. Okay, gives us 2.00, basically 2. all right, and that's correct. If I set it to 4, it should give us 4. Yes, if I set it to 2, it should give us 2 times 4, 8. Yes, and recall, basically this is testing our assumption here, or what we immediately realized based on the definition of this rectangle estimation, that for any constant function, the integral is just the value times b minus a, right? So if c is 2 and a is 0, b is 4, then we get 2 times 4, which is a. All right, now let's try some other function, but first I'm going to change the name of this interface. So refactor rename, I'm going to call it integral function 1D. okay, finish it. So in the integral we also have integral 1D, alright, and here we also have that. Now if you recall, I mentioned there is a built-in function interface. So function T1, T2 interface. So let's call it function Java util function. So T and R, which is double. The first one, T, is the input type, and the R is the return type. Func is equal to, basically T goes to 2. Okay, let's call it func1. So we're using lambda expression. And here what I'm going to do, I'm going to basically have the same code here. Func1 integral finder func1 result 1. I'm going to return the result. But what I'm going to do here, I'm going to go to the integral 1D and define another constructor based on let's also remove this, based on this function interface. So function tr, I'm going to pass double func, and basically what we're going to do here, we're going to say that t goes to function dot apply t. So I'm basically doing a conversion here, but it's just because this function interface is built in, it's most likely that another person knows about this. So I'm just saying that, okay, if the user uses this one, my constructor just converts it to my integral function. It's not the cleanest way, but this type of adapters or conversions are typical in this case. All right, and we go here, integral finder 1. Let's test that this works. It does not work. Let's see why. All right, I'm going to it's calling a native method to a double. So apparently it's not able to do the conversion here, and I guess let's see if we can define this as a, so this dot func equals new integral function 1D. Let's see if we can define it as an anonymous class, and then we are going to return apply x. Let's see if this works. No, it still cannot work. Bad type on operand stack. Alright, apparently this interface doesn't work. Function double double. It should return a double, and okay, so if it returns the double class, we get the double value. Let's see if this works. I think the problem is with the type conversion. No, it still doesn't work. So maybe the types are different. That's a little bit strange for me, but okay, we can stick to our basic definition of integral function 1DR interface. Alright, so right now I'm just going to remove this. Maybe later on I'll try to test to see what's going on here. But this works, so our test 1 is going well, right? Now let's do test 2. In test 2, I'm going to set this to t. So, and here test 2, and I already know the so the forward approximation is equal this, and then we also do a sysout. Exact result is equal to double exact. So let's maybe do the double start is 0, double end is 4.0. Here we put a start and end. Exact is x squared over 2, so 0.5 times end minus start times start, and we put this here. So we just want to compare these. So the forward approximation here is 7.92. The exact result is 8. So the error is pretty large, and that's not good. And the way we reduce the error, we increase the number of terms. So instead of 100 terms, 100 subinterval, I'm putting 1000 subinterval, and I get 7.992. Still not good enough. Still, it's close, but it's not good enough. Now the problem with rectangle approximation is that if you look at the error, all right, the error of the rectangle approximation is proportional, linearly proportional to the delta, or the length of the subinterval. The smaller it is, the smaller the error. All right, so if I, instead of 10 subintervals, I have 100 subintervals, so increase the number of subintervals by 1 order of magnitude, I reduce the error by 1 order of magnitude. Now this is not good, because then I have to increase the number of subintervals by a very large number to get a very good error, or a very small error that I want. All right, so rectangular approximation, if I reduce delta by 1 order of magnitude, or increase the number of subintervals by 1 order of magnitude, the error goes down by 1 order of magnitude linearly. Okay, now a better way is Trapezoids method. So the Trapezoid method gives exact result for any first order linear function. And if you recall, the rectangle method gives exact result for a 0th order or a constant polynomial. So the first order, the trapezoid method gives exact result for a first order polynomial or any linear polynomial, any linear function. And again, we assume that it's uniform partitioning, and in each subinterval, what we actually do is, let me just copy and paste this here. So basically what we do, if you see here, it's a linear approximation. So we take these 2 points at the beginning and end of the interval and we connect them by a line. So we are approximating this function by a line in this interval, and we calculate the area under this line, which is the area of this trapezoid. That's why it's called a trapezoid approximation, because it's based on the area of these trapezoids. All right, and the trapezoid the area is the small base, which is f of xi, plus the larger base, which is f of xi plus 1 divided by 2 times the length of the connecting line, which is delta. All right, so this length, you average them out, you average the two and times the length of the interval. And again, this considers a linear approximation of fx, and the reason I'm putting emphasis of this linear word, because this, as you will see later, is that this is the basis of how we come up with a general method, which is called the quadrature method for calculating or numerically calculating integrals. The foundation is here, that if we can have a method that gives us the exact result for some polynomial of some order, so order 0 and order 1, right? Rectangle is only order 0, trapezoid is order 0 and order 1, or in general any order 1. Then if we implement this kind of integration or this kind of area approximation, it turns out the trapezoid has an error which is proportional to delta squared, or 1 over n squared. Now this means that trapezoid has a smaller error compared to rectangular. So in trapezoid method, if I reduce the length of the interval by 1 order of magnitude, my error goes down by 2 orders of magnitude instead of 1. All right, and this is very desirable. Now obviously, compared to the rectangle method, we have to do more evaluations of the function. We have to evaluate the function both at the beginning and at the end of the interval. But the thing is that we already do that for the rectangle too, right? Because we have to evaluate the f at the beginning of each interval. And then the end of one interval is the beginning of the second interval. So in theory, the number of evaluations of the functions are basically the same, right? So we're gaining 1 order of magnitude better approximation or a smaller error at basically no additional cost. Okay? So that's a very good thing. And so let's head back to Eclipse and try to implement also the trapezoid method. Before that, I'm going to also implement the backward approximation. So forward rectangle, backward rectangle, and in the backward rectangle, what we're going to do, we're going to xi's are still the same. So in each sub-interval, in each interval, I'm going to calculate the function at the end. So this should be I plus 1, right? So we still have n terms, but the first term is start plus delta, not the start minus delta. And start plus delta is the end of the first interval. Start plus 2 delta is the end of the second interval. And everything else is the same. Now we can also combine these two for terms. We don't need to separate for loops. We can have just one for loop. So if I put this double before the for loop, and then also move this back here, and then I don't need this, and I really don't need to also have an array here. I just can have xval, okay, and here we just put terms, and I don't even need to have this. I just put it directly here. So this is the exact summation definition of Riemann integral. This is the exact definition of Riemann integral. And delta times the value of the function at start plus I delta. Let's copy and paste these. We put this I plus 1 here. So we're calculating the function at the end of interval. Evaluation at the end of interval. Evaluation at the beginning of the interval. Okay, so let's go back here. In test 2 we have the result. Here let's also create a backward approximation, so let's call it result backward. Instead of forward rectangle, I'm going to call backward rectangle. Okay, let's make it lowercase. Okay, so we have our integral function start to end. Let's go 100 terms, and forward approximation, forward rectangle, backward approximation, backward rectangle, and exact. And as you can see, because this linear, if I go back to the slides here, the forward approximation underestimates the area in each sub-interval, right? The area of the rectangle is smaller, maybe here, for a linear curve. For a linear curve or any curve that is increasing, the backward approximation actually overestimates the area of the under the function in each sub-interval. So the area of the rectangle is actually higher than for the backward approximation, the area of the rectangle is higher than the area under the function. So the backward approximation for this function t is overestimating the result, the exact result. Now what you can see is that this is 7.92, this is 8.08. So there is the error is 0.08, and the error is exactly the same for both forward and backward. And you can mathematically prove this, that the forward and backward basically have the same error here in this case. All right. Now the last thing we're going to do is do the midpoint approximation or center approximation. So in the center, we still have delta. We evaluate the function at the center point, which is the start point, I delta, end point I plus 1 delta. So we have I plus half delta. And let's go back here. So we have the forward, we have backward, and now we do center. And you probably can guess that in this case the center should have an error which is half of the forward and backward. So result center approximation. Instead of having backward, I'm going to do center rectangle. All right. So in this case, it's actually giving the exact value. So the error is practically 0. Now let's change this to t squared. 21 so the exact, and then if we do that, all right, I'm going to use another test case here. Test 3, which is t times t squared, and the exact is x cubed over 3. So we're going to have n times n times n minus start times start times start divided by 3. And here I'm going to run test 3. 21.0144, 21.654, 21.333. So the forward approximation, the error is about 0.02. to 1, and the backward approximation is the error is about 3. No, so the forward approximation, the error is maybe let's just calculate also the error. So I'm going to put here sysout forward error equals plus basically forward approximation, okay, result minus exact, and then I'm going to have backward error, which is result backward, and then I'm going to have center, result center. Minus 3.2, 3.2, and minus 5 e to the negative 4. And as you can see, the center has much better performance than the others. So it's wise to always use the center approximation instead of forward or backward. And the main reason is that when we do center approximation, actually this so the center approximation, what it does is, let me just maybe zoom in each subinterval, the center approximation it doesn't overestimate, and also it doesn't underestimate, right? So what happens here is that the area under the blue curve is what we are looking for, and the center approximation has some part which is higher than the curve and some part that is lower than the curve. So there is a good chance that these two actually cancel each other out to some very good degree. So what happens is that the area of this rectangle becomes much closer to the actual area under this curve, right? So the center approximation actually has an error which is 1 order of magnitude better. So the center approximation, the error is basically delta squared. Let's call this symbol. The center approximation has a better error than the forward and the backward. All right, and so these are all the rectangle method. In the next lecture, I'm going to start with the trapezoid and other numerical ways for calculating the integral. Thank you for watching, and I'll see you in the next video.